So we know that the potential is 0 if the current is constant. What happens if the current changes? So let's start with a circuit. Here's our inductor. Let's say that the current in our inductor is coming up on this side, going down in the back and up in the front. So if we're looking at our inductor like this, it's coming up in the front, down in the back. So then the magnetic field of the solenoid is pointing towards the left. So there's the current I. The magnetic field created in the solenoid because of that current points down the length of the solenoid. Okay, so we put this current through this solenoid, it makes a magnetic field that points that way. That's stuff we've done about solenoids already. But now let's take that current and let's increase it. So we're going to increase the current I, because we're asking what happens in our circuit if we change the current. So we're going to increase current I. If we increase current I, we're increasing the strength of the field that points this way. If we're increasing the strength of the field that points this way, we must induce a field that points the other way. And that comes from Lenz's law. So if we increase I, we induce B to oppose the change. So this is our induced magnetic field. It opposes the change that we made. If we have an induced magnetic field, well, we know that that induces the current. And that induced current is going to be opposite the direction of this current because those fields are in opposite directions. So our induced magnetic field, so the current we originally had comes up in the front, down in the back. Our induced current is going to come down in the front and up in the back. So it's going to be opposite in direction. So our existing current came up in the front, our induced current comes down in the front. And it has to be opposite, so we get those opposite magnetic fields to oppose the change. What does that mean with regards to potential? Well, if we ask what current does, current is the flow of positive charges. So our induced current and current is flow of positive charge. So it moves positive charge towards the left end of the solenoid or the left end of the inductor. So here's where it might be a good idea to go back and review some of that stuff we did when we began Faraday's law. You remember we moved the slider through the magnetic field. Each of the positive charges felt a magnetic force that drove the positive charges to the high end of the bar and the negative charges towards the low end of the bar, which established an electric field which pointed from the top to the bottom, and an electric potential which was higher at the top and higher at the bottom. Same thing happens here. We drive the positive charges to this end, the negative charges to this end, which leaves this end at a high potential and this end at a low potential. So let's label that on our diagram. So this end has our high potential. This end has our low potential. So overall, we get a potential difference over the two ends of the inductor, which we'll call delta V. So we get a potential difference across the inductor. now what we'd like to do is find that potential difference using Faraday's law. So now we've established how we get the potential difference. Now let's get some details about that potential difference. So delta VL, potential difference across inductor. So now let's apply Faraday's law. Remember, Faraday's law says that the induced potential, okay, and this is our induced potential. So Faraday's law says our induced potential, which we've called delta V of the inductor, is minus the change in magnetic flux with respect to time. Well, what's important in this equation, minus means that the induced potential, the induced current, and the induced magnetic fields all oppose the change. The next thing we can do here is this is our total magnetic flux, and we could write that in terms of our inductance L. We know that inductance L is the total magnetic flux divided by the current, so our magnetic flux is going to be inductance times current. L is a constant, so that can come out front. So this tells us that the potential difference over the two ends of the inductor is minus L di dt. Okay, what about a couple of details about that? Does that make sense? And what does the minus sign tell us? So what it says is that, let's just apply it to thinking about this. If we increase I, then our slope, our rate of change of di dt, that's positive if our I is increasing. And it says that our induced potential, delta V, so our induced potential decreases, our amount of potential decreases as you go in the same direction as current. So as you move with the direction of the current, you get to a lower potential. So that's what happens if we increase the current. What if we decreased the current? Does our equation still hold? So is that still true? So let's look at the case of a decreasing current. So we'll still have the same setup. Let's have our current still flowing in the same direction. Let's have it going upwards. So our current I is this way. But this time let's have I decreasing. So that current I makes this magnetic field B. If we decrease I, we decrease B. So what is the induced magnetic field that we get? That induced magnetic field would have to match this field, because if this field is getting weaker, then we'll have to make more field that points in the same direction to keep it strong. So there's our B induced. If our B induced is in this direction, then our current induced would have to be in the same direction. So our induced current would have to match our existing current. There's our induced current. Let's see how that settles with Faraday's law. If we write down Faraday's law, then our induced potential, delta V, our induced potential of the inductor, is minus inductance, di dt. If we decrease I, then di dt is less than 0. If it's less than 0, then our potential gets bigger as we go with current. And that matches what happens in our diagram. As we go with the induced current, this induced current carries positive charge, going back and goes down in the back, up in the front. So it transfers positive charge to this end. That's where we get the high V. And it leaves negative charge at this end. That's where we get the low V. So we get a delta V between the two ends of the inductor, where this is the high end and this is the low end. So Faraday's law gives us both the magnitude of that induced potential, L di dt, as well as the sense of which end has the high potential and which end has the low potential. Okay, we're going to start using this with examples soon.